Okay, in this lecture, we'll talk about the energy of chemical reactions. So I want to start with this idea of enthalpy. Enthalpy. It's a little odd. So I'm going to scroll back and scroll forward in hopes that my computer catches up. There we go. So when a chemical reaction takes place, we'll have bonds break and new bonds form. And the breaking of bonds is going to require energy. And when we form bonds, it's actually going to release energy. So if we look at this chlorine-chlorine bond right here, if we need to break this apart, we're going to have to put in 58 kilocalories for every mole of chlorine we have. And that's the amount of energy it's going to take to rip those two apart. Now, if we have two separate chlorine atoms and we're bringing them together and hoping they form a bond, then when that bond forms, so these are coming together this time, it's actually going to release 58 kilocalories of energy. And so we'll describe this energy being absorbed and released as enthalpy. And enthalpy is going to be abbreviated with this fun variable, delta H. And that delta symbol, again, the triangle means change. So the change in the enthalpy, that H is enthalpy, is whatever energy is either absorbed, so that will happen when we need to break a bond, or released, which will happen when we form a bond. And it's the heat of the reaction, or the enthalpy change. So when we have energy absorbed, our enthalpy change is going to be positive. It's going to require that we put energy in. And when it's released, when we form this bond, then our enthalpy is going to be negative because it's going to lose that heat out into its surroundings. So if you could hold this chlorine atom in your hand, and in your hand you felt what happened when it broke, it would feel like it got cold if the bond breaks, because it will require energy, and it's going to take that energy from you. And so it'll feel like you're losing energy or getting colder. If you're holding it when those two chlorine atoms come together, then it's going to feel like it's getting hotter to the touch, because you're the surroundings, you're the thing around it. And so if it's going to release energy, you're going to feel that energy that's going away from the molecule that's forming. So we like to track reactions with what we call energy diagrams. An energy diagram is going to plot energy on the y-axis, and then something we call the reaction coordinate on the y. You can think about it as time too, or the progress of the reaction. And so in this case, there's a few things we're looking at. We plot the energy of the reactants relative to the products, and we're not going to rely too heavily on quantifying exactly what those energies are, but look at them relative to one another. Then we have an activation energy right here that we abbreviate E subscript A. And then we have the enthalpy that we just discussed, and that's the difference between the energy of our reactants and the energy of our products. So our activation energy is this barrier that needs to be overcome. For a bond to break and a new one to form, this transition state will have a partially broken bond between A and B and a partially formed bond between C. And this is the most unstable arrangement within the reaction. And so it's high in energy. And so our reactants need to be able to have enough energy to make this happen. And if they do, if they get up to this energy, then they can form our products and come down to this lower energy here. And so these reaction diagrams have the component of the relative energies of our reactants and products, our enthalpy, and our activation energy described in it. This is going to look different for different types of reactions. Some reactions give off energy and some do not. And the difference between these two is the relative stability of the products versus the reactants. So in a reaction where the products are more stable, then they'll be at a lower energy than our reactants. And if they're at a lower energy than our reactants, then our enthalpy, our change in the heat of the reaction, is going to be negative. That really means that heat is going to be released. So if you're near this reaction, it's going to feel like it gets hot because it's giving off that heat. And these types of reactions that give off heat, that release heat, because remember, you're absorbing to break the bonds in your reactants, and you're releasing energy to form your products, and you're going to release more energy to form your products because they're more stable. So you're going to have what we call an exothermic reaction. So exothermic energy is exiting the reaction or the molecules. Now, the opposite is when our products are less stable than our reactants. And in this case, they're going to be at a higher energy level than our reactants. And so that means that for the reaction to take place, it actually needs to absorb heat. And if you're holding it, it's going to feel like it's getting colder. And the reason it's going to feel like it's getting colder is because it's absorbing heat from you. It's stealing your heat. And so because these are less stable, they're going to release less energy than we had to put into making our reactants. And our enthalpy, it's going to be positive. And we call these reactions endothermic. And I don't have a good way of remembering this other than it's just not exothermic. If you come up with a good mnemonic device, please let me know. So we'll look at two different types of reactions, exothermic and endothermic. Exothermic will release heat, endothermic will absorb heat. Here's a summary slide for you for studying later that compares an endothermic reaction with an exothermic reaction. So remember, our exothermic reactions are going to have these negative enthalpies, and they're going to feel like they're getting hotter, and they're going to have stronger bonds in their products. Our endothermic are going to have positive enthalpies. They have weaker bonds in their products, and they have to absorb heat for them to for the reaction to take place. And this enthalpy difference right here is just whatever the difference is from the energy of the reactants to the energy of the products. So if it's endothermic, it's this right here. Here's my enthalpy. And if it's exothermic, it's this difference right here, my enthalpy. And so this is less than our reactant, so it's negative. This is more than our reactant, so it's positive. Let's look at a quick way that we could do calculations with this. For every type of reaction, we'll have an enthalpy associated with it. So this is the enthalpy of the reaction, or the change in heat of a reaction for the combustion of octane. This is what would take place in your car. So combusting octane will release, and I know it releases because it's got a negative sign. So this is an endothermic reaction. It'll release 5,471 kilojoules of energy. It's a lot of energy. So my reaction diagram would have my products, which is my carbon dioxide and my water, at a lower energy than my reactants, which is my oxygen and my octane. And so this right here would be my activation energy. And right here, this is my enthalpy, that negative 5,471. So if I had a gallon of gasoline and I wanted to know how much energy I got from it, I could figure that out using that enthalpy. Now, a gallon is about 2.6 kilograms, which is 2,600 grams of octane. So I'm going to start there with this mass. If I have 2,600 grams of octane as my starting point, and I want to convert into units of kilojoules, I am going to use my enthalpy as a conversion factor. And the way these are usually reported is negative 504 or 5,471 kilojoules per mole. And this per mole is really the mole of the reaction. So this whole reaction right here is going to, I'm going to call this a mole, a reaction mole. It's going to produce this 5,471. So for each 5,471 kilojoules per mole of this reaction that take place, 2 moles of my octane react, 25 moles of my oxygen react, 16 moles of carbon dioxide are produced, and 18 moles of water are produced. So I can have these conversion factors that 1 reaction mole equals 5,471 kilojoules, and that's coming from my enthalpy. I also know that one reaction mole is going to require that 2 moles of my octane react. Now I have mass of octane, not moles, so I'm probably going to need to use my molar mass of octane as a conversion factor as well. And if I calculate that from the periodic table, it's 114.23 grams of octane will equal 1 mole. So now I can calculate this. I'm going to start with my molar mass, and I'm going to use that as my first conversion factor to calculate the number of moles of octane I have. Now, once I have my moles of octane, I'm going to either build a conversion factor or do 2 separate conversions. So the 2 separate conversions would look like 23 moles of my octane as a starting point, times the number of moles. So if I'm in moles of octane, I want to be in reaction moles. So I'm going to go 1 reaction mole divided by 2 moles of my octane. And then I want to convert into joules, which I can do with this enthalpy. So times 5,471 kilojoules, it's negative, by 1 reaction mole. So these are going to cancel my reaction moles. My moles of octane will cancel, and I'll be left with units of kilojoules. And that's going to equal negative 62,000 kilojoules. I can combine these into 1 conversion factor, which is to say that if I have 5,471 kilojoules per mole of my reaction, I really have 5,471 kilojoules for every 2 moles of my octane that react. And that's how I can calculate the energy in joules from the mass or the number of moles of one of my reactants or products in a reaction, as long as I know that enthalpy. All right, we'll stop there. In our next lecture, we'll look at reaction rates.